In this video, we're going to calculate the force on the human eardrum. And we're going to do it for two types of sounds. A sound with intensity of 120 decibels, which is the threshold of pain, so a very loud sound. And the intensity of the faintest sound that good human ears can hear, 0 decibels, which is 1 times 10 to the minus 12 watts per square meter. So, of course, pressure is equal to force divided by the area, and that can then be solved for the force, which is pressure times area. In the case of an eardrum, it would be the maximum force on the eardrum would be the pressure difference between the normal atmospheric pressure and the maximum pressure attained by a sound wave times the area of the eardrum, which is about 50 square millimeters, about 0.7 centimeters squared. 0.7 centimeters squared, that gives you about 50 square millimeters. Now, remember that on the eardrum on one side, it's equilibrium pressure, about atmospheric pressure. On the other side is exposed to the air, and there you have the pressure differences. So we want to catch it at the maximum pressure difference as it varies away from the equilibrium point. The equation we use to find the maximum pressure difference, of course, the square root of 2 times the density of air times the velocity of air times the intensity in watts per square meter. So taking the first one over here at 120 decibels, we plug in those numbers, and so for 120 decibels, we get the delta pressure maximum to be equal to the square root of 2 times the density, which is 1.29 kilograms per meter cubed, that's of course mass per unit volume, times the velocity of sound in air, which is 340 meters per second. And then, of course, we have the 1 watt per square meter for the intensity. And that gives us the pressure difference of a sound at 120 decibels. So let's find out what that is. That kind of makes me think. You know, we have these devices that can actually measure the intensity of sound in decibels. And really all they are is devices that can measure pressure difference in the air, which then translate to, of course, the equivalent intensity. So that's how those devices work. All they do is just measure the pressure differences caused by the sound waves. Anyway, multiplying this, we get 2 times 1.29 times 340 and times 1, well, and take the square root of that, we get 29.6. And of course the units, this is pressure, delta P max, pressure, that's equal to pascals, or 29.6 newtons per square meter. That's quite a lot of pressure difference caused by a very loud sound. Now we're going to do the same for 0 decibels, which is the very faintest sound that the human hearing can hear. And so there we have the dP max, the delta pressure max, which is equal to the square root of 2 times 1.29 kilograms per cubic meter times the velocity of 340 meters per second. And finally, the intensity, of course, for 0 decibels is 1 times 10 to the minus 12 watts per square meter. So that's going to give us a much smaller pressure difference. Let's find out what that is equal to. So 2 times 1.29 times 340 times 1e to the 12 minus equals, take the square root of that. Wow, that's a very, very tiny pressure difference of 2.96 times 10 to the minus 5 newtons per square meter. Notice the enormously small pressure difference caused by a very, very faint sound of 0 decibels. And yet, if you have good ears, you can actually pick up that sound and notice these enormously tiny pressure differences from the normal air pressure. Remember, normal air pressure, P atmosphere, is equal to 101,300 newtons per square meter. And notice how much smaller is this compared to that. It's an extremely small fraction, and yet human hearing can pick up that pressure difference and turn that into sound in our brain. Absolutely amazing. But now, let's find out what the force then is on our eardrums. So in the case of 120 decibels, the force max experienced, of course, the force will oscillate with the pressure differences. So this is equal to the delta P max. The delta P max we found was 29.6 newtons per square meter, and we have to multiply that times the area of an eardrum, which is about 50 square millimeters, convert that to square meters, so we need square meters on top, millimeters on the bottom. 1 meter is 1,000 millimeters, and of course 1 square meter is 1,000 millimeters squared. So 29.6 times 50 divided by 1,000,000. 1.48, so the force max that we feel in our eardrum is equal to 1.48 times 10 to the minus 3 newtons, which is 0.00148 newtons. So about 0.15% of a newton. Very small, but yet that's a very large force felt by the eardrum when the sound of 120 decibels is present. Okay, what about the faintest sound? Well, F max, so at 0 decibels, F max is equal to the pressure difference, which we calculated to be this, so that would be 2.96 times 10 to the minus 5 newtons per square meter. And of course, converting that to 50, and then we have the area of the eardrums converted to square meters, which is 1 over 10 to the 6th. That would be millimeters squared and meters squared, like that. So what would that be equal to? 2.96 e, let's do it again, 2.96 e to the 5 minus times 50 and divide by 1,000,000 equals, and here we have a maximum force through those pressure oscillations of 1.48 times 10 to the minus 9 Newton. So 1.5 nanonewtons of force on the human eardrum, and yet we can make sound out of that. Just imagine the enormously small amount of force required for the human ear to pick up that very slight pressure difference in the air and turn that through the mechanism of the ear and the brain to turn that into sound. Quite amazing, but that's how it's done.